did that again, but made the rectangles smaller, would it be more accurate?
Yes.
Yes, going back to that same idea. If I made them smaller again, would it be more accurate?
Yes.
The amount of calculations that you would have to do for each rectangle, if you made them smaller and smaller, would be painful. Yes? There's no question. So there's got to be a nice little maths thing that we do here. Now let's have a think about this. If I make these ones smaller, what we call that, it's a change in x, okay? Or we call it delta x. So this thing here is our delta x. So if we make this delta x smaller and smaller and smaller, if we think about it, our area was our f of x times x. Yep. F of x was our height. Whoops. That was our height. This was our base, okay, or our width. Yep. So that's how we found our area. If we make our x really small, we're still going to go like this. So this is a small x. Yep. So my height times this. Now, if you think about this, that's delta. That's our Greek thing. If I wrote something like this, f of x dx, okay, where have you seen those two written like that before? Yes. Jazz has gone like that. Remember we found the antiderivative?
Yeah.
So if I think this times this times this, that part there. Now what is that? This squiggle is our derivative or our antiderivative or our integral sign. Where does that come from? Now, I'm just going to go back a bit here. We had to add up all of these, didn't we? We had to add up the areas. So if we add up the areas, we come across this, that's the sum. So it's the sum of f dx times that. So that's another Greek symbol, means the sum. So that means add all those little areas up. So that's what that means. And then, instead of doing it, it comes down to a nice little thing of what we call the integral. If I was to find the integral of this, I would say it's between 0 and 2, because that's where my integral is, between 0 and 2. So, I go back over here. So I have this thing called the integral, between 0 and 2. That's what I wanted to work out. What was my f of x for this one here that we've worked out?
X squared plus 1.
Was x squared plus 1. There's my f of x dx. So this part here comes from all of this. We're summing up all the little triangles, all the little rectangles, okay? And this is our sum. That means do it by hand. This is our shortcut way of doing it. What's our antiderivative of this?
X cubed on 3.
Plus 1x plus c.
Plus x
Plus 6.
plus c. Okay. That's what we would normally do. I'm going to leave the c there for the moment. Okay. We do this, we put our 0 and 2 in there. When we did our overestimate and our underestimate, okay, one's above, one's below. So it's like we're taking them away from each other. So if I sub in 2 into this, I do about 2 cubed, put my C in there, minus where I put everything, my 0 into here. Just going to write it out now. Put our 0. So if I do this, I end up expanding all this out. That's going to be 0, 0, 0 minus C. Those C's cancel out. And I'm left with 2 to the power 3 over 3 plus 2. Now what's that going to equal? That's 8 divided by 3 plus 2. That's it.
4 table 3.
Okay.
It's a 4 table 3.
4 and 2 thirds.
What's that?
4 and 2 thirds.
4 and 2/3, which is 4.66, so I'll put it at 67.
Oh.
What did we get our estimate of our area under the graph to be? We got it, our estimate was 4.75. This is the exact area under the graph. So this is our exact area. So if we go back to that question, our exact area is found like this. Now when we do these, do you think we have to bother with the C? We don't have to bother with the C because every time you're going to have a plus C on the end, you're going to have a subtract C. So they're going to cancel each other out. You can put them in, but most times when we do what these are called definite integrals, we actually leave them off, the C off, because it's going to cancel out. So this is called a definite integral. Now, what we've got here, this is the function y equals x squared. Okay, on the bottom of this sheet, I've got the link to this little thing here. So if we have a look at this, if I just worked out the area of these rectangles, I would get the sum of 14. That's our underestimate, okay? It's from 0 to 4 of x squared. Our actual one would be 21.333 if we went and worked it out. Keep an eye on this and keep an eye on this as I make the rectangles smaller. So now it's got closer to 15.3. Okay, it's getting, so you can see as I make it smaller and smaller, it's getting more accurate and accurate. This is what this part is doing. This one here is this fella, Reinman. Okay? He is adding them up, doing that working out. So this poor fella Reinman is sitting there, you know, in the web going, okay, I'll quickly add these all up for you. And he's getting that for us. Okay? So Newton in the meantime is sitting here with his integral. He's worked it out the exact value. This fella's going, okay, I want to get closer to you. I'll keep getting closer and closer. So I could keep, my slider here is not going to let me get further. But every time, this is going to get closer and closer. That's his underestimate. If I swap to my overestimate, it's 22. So if he did the overestimate, the underestimate, average them out, he's going to get closer to this. So what you need to be able to do is, one, you need to be able to figure out where do I match the pairs for these? Where do I find my points to sub in? Whoops. Yeah, that's not the one I want to move. There you go. Now, so if I asked you to find the approximate area under the graph, or an exam question did, then you have to have a look. This is my first point of my rectangle. Does that make sense? So I've got to use that value to find my height. My width would be 1, and then whatever my height was, this is x squared, so I know it's going to be 1. This one, this is my value, so that would be sub in x equals 2. That's my value there. So the only trick between your overestimate and your underestimate is picking the right points. Okay, so if I go to the lower one, I've got to look at my graph and think, okay, it's that point there, it's that point there. I've got to match it with that one, I've got to match it with that one, match it with that one. Yep. When we're finding the exact value, we find our integral. So I'm going to come back and do a couple more examples on the integral, but on here, there's a couple of exam questions. These actually come from a Year 12 exam. Okay? So this is the stuff that you'll be examined on in Year 12 as well as Year 11.